So in our first case, we've got a function f of x equals x to the 2/3. And this is asking us to find the Taylor polynomial with degree 3 centered at a equals 1. So let's find the third degree Taylor polynomial. Okay, to do this, recall we need, since we're finding the third degree Taylor polynomial, we need to know the derivatives up to the third derivative of our function f at the value a. So we'll first work out what f of 1 is. We're going to need to know the derivative. That's 2/3 x to the negative 1/3. So f prime of 1 is 2/3. We're going to need to know the second derivative. X to the negative 4/3. So f double prime of 1 is negative 2/9. And f triple prime is 8 over 27 x to the negative 7/3. So f triple prime at 1 is 8/27. And now we have enough information to construct the Taylor polynomial. So from this stuff here, we get that the third degree Taylor polynomial, well, that's just going to be f of 1 plus f prime of 1 over 1 factorial x minus 1 plus f double prime of 1 over 2 factorial x minus 1 squared plus f triple prime at 1 over 3 factorial x minus 1 cubed. And we know all those derivatives now, so we get that this is 1 plus 2/3 x minus 1 plus, well, we have a negative 2/9 on top divided by 2 factorial, which is 2 on the bottom, so that's an x minus 1 squared, and then plus an 8/27 on top divided by 3 factorial times x minus 1 cubed. Now, let's just write down what these are. This is 2/3 x minus 1. The next one, the 2's will cancel, so this becomes a negative 1/9 x minus 1 squared. That's a 6 factorial on the bottom. I can use a 2 to cancel with part of the 8 to leave us with a 4, and then the bottom would be just 3 times 27, which is 81 x minus 1 cubed. And that's our third degree Taylor polynomial. Okay, so there's our Taylor polynomial that's representing our function, or an approximation to our function at the value a. Okay, so we could check this. I mean, it's always nice to see that we can check these results using things like Wolfram Alpha. And one of the things we can type in is just Taylor polynomial of, and what it will do is it'll come back with some fillable fields that we can enter in some of our information into. We'd like to include the order of the Taylor polynomial as well, so we'll click on that button. So we have 3 fields to fill out: the function, we want the center point for the expansion, that's 1, and we want the order is to be 3. So now we can. So what we found is that the series expansion at 1, which is of third degree, is here. The coefficients are 1, 2/3, negative 1/9, and 4/81. That's exactly what we found out. So if we skip back here, that's exactly what we got as a result. So you can use things like Wolfram Alpha to check your results or compute your Taylor polynomials. What it's doing is exactly the process we're doing here. Okay, so we've got this Taylor polynomial. What does it mean? What does it represent? Let's try to come up with some sort of visual representation of this. So there's our function. The point we're interested in is 1 comma 1. Okay. So that's the point we're going to construct our Taylor polynomial at. So find a degree 3 polynomial that approximates the function close to that point. And we already worked out what that Taylor polynomial was. But in GeoGebra, which is the program we're using here, there's a built-in Taylor polynomial command. So Taylor, and it says what it needs is a function. So we'll use our f of x that we just input. It needs a value, that's the center value, which is 1, and then it needs an order, so that's 3, and we hit enter, and it's constructed the third degree polynomial. Let's just color it a different color so we can distinguish it from the actual function. So color it red, let's say, and let's also show its name and value. Okay, so we see that the polynomial that's just constructed is this polynomial here, which agrees in value with the coefficients we've got. They've just done some rounding here and entered it as decimals, where we've left ours as sort of exact values. Okay, so the question is, well, it looks like the polynomial is a good approximation to the function nearby this point, nearby the point 1, 1. The polynomial, which is the red curve, and the function, which is the black curve, are very close to each other. Of course, they pull away later on, so it means that as the x values increase, the third degree Taylor polynomial doesn't approximate the function very well, but it does close by. Now, in our particular question, we want to determine how good the approximation is close by, particularly on the interval 0.8 to 1.2. So let's just see where those values lie on the real line. And so what we're interested in is on this little interval, how close is the red curve to the black curve? So let's zoom in a little bit on it. Okay, it looks like they're pretty close. How close are they? Well, they're not actually lying on top of each other. If we zoom in close enough, we'll see that the red curve starts to pull away from the black one eventually. Keep zooming in, there we go. We start to see them pulling away. So they're not actually equal to each other. The question is how much of a difference is there between the red curve and the black curve? How much of a difference is there between using the polynomial values and using the function values? That's what the remainder's capturing. It's capturing that distance between those two curves. And we want to have a bound on how big that distance is. Or maybe I should say how small that distance is, because we're interested in a small distance. Well, that's what Taylor's inequality allows us to do. It allows us to get a bound on that distance. So that's this next part. Use Taylor's inequality to estimate the accuracy of using the polynomial. In this case, it's the T3 polynomial. So let's get an idea of that. Okay, so what does Taylor's inequality require? Let's get back and take a look. Taylor's inequality says you have a bound on the remainder, which depends on the nth plus first derivative. So in our case, n is 3, so this would be the fourth derivative. I need to know what the upper bound is and the magnitude of the fourth derivative. And the rest of the information we know. We know what n is, we know what x minus a will be. It'll be at most 0.2 in this case. Okay, so let's go to work on finding that m. Well, that means we need to know the fourth derivative. So we've got all the first three derivatives computed. To get the fourth derivative, we just take the derivative of this piece here, which is negative 56 over 3 to the fourth, x to the negative 10/3. And we're actually interested in just the magnitude of this. So that is 56 over 3/4 x to the negative 10/3. And how big can this be? How big can this be? Well, it's at most what? Well, notice that the x has a negative exponent, so the x is really, you can imagine it as being in the denominator. So this is really a decreasing function. it's a decreasing function, and so the biggest it can occur, the biggest value it takes on the interval 0.8 to 1.2, the biggest value that it takes on will have to be the value at 0.8 because it's the function's decreasing. So this is at most f of 4 at 0.8. And this is on the interval, so on x, the interval from 0.8. And we can include these things to 1.2. The biggest value occurs at the left-hand endpoint. And so now we just work out the fourth derivative at 0.8. That means plug it into here, take the magnitude, and we get that that's approximately 1.45458. You can work out some more decimal places if you want. That's about as much as we really need. And this is going to be our m value. So m we're going to take to be 1.45458 ... So that's our m value. That's the bound on our fourth derivative. So now we can use Taylor's inequality. Oh, I probably should indicate that we got this inequality here. Though I said it, I didn't write it down, since f fourth is decreasing. That's why we knew the maximum occurred at its left-hand endpoint. If we didn't know it was decreasing, how could we figure out where its maximum occurs? Well, we have optimization techniques from Calculus 1 that we could use to find a maximum. In this case, it was decreasing, so we knew it appeared at the endpoint. The maximum appeared at one of the endpoints. Okay, so now, by Taylor's inequality, we have that the remainder is at most m over 3 plus 1 factorial x minus 1 to the 3 plus 1, which is at most 1.45458 over 4 factorial. And the biggest x minus 1 can be is, well, we're looking on the interval from 0.8 to 1.2, so the biggest x minus 1 could be is 0.2. And the power there is 4, and this is approximately 0.000969971 ... And so what we've found is that our remainder, I should indicate here, that our remainder in using the third degree polynomial to approximate the function, that remainder is bounded above by this number when x is in the interval 0.8 to 1.2. Okay, so let's again look back at our sketch. What we just found was, okay, so the red curve and the black curve, the red curve being the Taylor polynomial and the black curve being our function, they're pretty close. How close are they? Well, in this interval, the red curve and the black curve are within 0.000096 ... of each other. Of course, that's not true when x is outside of that interval. We can see as we go along and x gets bigger and bigger and bigger that the polynomial and the curve pull away from each other. So the error, the remainder between the two, the difference between them is bigger. But on the interval from 0.8 to 1.2, the difference between the polynomial and the function is at most 0.00009. So therefore, using the third degree Taylor polynomial, it approximates the actual function, x to the 2/3, to within 0.000097 on that interval 0.8 to 1.2. So we know if we plug in a value of x that lies in this interval into the polynomial, we know the value the polynomial spits back at us will be within this error of the actual value of the function.